friends, in this video we are going to study about the static and dynamic error coefficients in control systems. In control systems, we have two types of error, static error and dynamic error. So first let us know that what is an error. Error is the difference between the input and the output of the system. So error is defined as the difference between the input and the output. Now this error, it can be of two types, static error and dynamic error. Now static error means, the word static means constant, okay, that is it is not varying with time. Not varying or not changing with time. Whereas the word dynamic means that it is changing with time. So static error means the error which we get which is not changing with time, that is it is static or constant. Whereas the dynamic errors, they changes with time. Okay. Now for control systems, static error can be calculated when we have applied the input as the standard test signals, and standard input signals are first we have unit step function, then we have unit ramp function, and third we have unit parabolic function. So if we have applied any of these three inputs, then the error which we have obtained is called the static error. Okay, because these functions, they are not changing with time, and the error which we are getting is also not changing, and the error is not a function of time. Okay, so this type of error is called the static error. Okay, now let us first find out that what are the static error coefficients. Okay, first we will study static error coefficients, then we will study dynamic error coefficients. So starting with static error coefficients. First, let us draw the block diagram of a control system, closed loop control system. Okay, closed loop control system has a feedback. So let us draw the block diagram for it. This is our input RT. This is the output CT. It is the error signal ET. Here we are having plus sign. This is minus. This is our open loop transfer function G, and this is our feedback transfer function H. So this is the block diagram of a feedback control system. Now, if we write the expression for the error for this feedback control system, then it will be error signal, that is ET, it is equals to RT, and here we are multiplying this output signal CT with this transfer function H. So here we are getting the signal as HCT. So ET will be RT minus, because here we are having the minus sign, so RT minus HCT. Okay. Now let us multiply this term CT with RT and also dividing it with RT. Okay, so there will be no effect if we are multiplying and dividing with the same term. So we will get ET equals to RT minus H. This CT upon RT, it is the transfer function, because transfer function is the ratio of the output and the input, and if we calculate its value from this graph, then CT by RT, it is given by G upon 1 plus GH. Okay, if we use the block diagram reduction technique, and we will find out that the overall transfer function of this control system will be G upon 1 plus GH. So this is the transfer function. Putting its value here, we will get G upon 1 plus GH multiplied with RT. Okay, so this we have got here. Now if we have this, then we will get the value. If we take RT as common, then we will get ET equals to RT is common. Inside we are left with 1 minus H upon HG upon 1 plus GH, and this is multiplied with RT. Okay, let's solve it further. We will have RT, then this 1 plus GH minus GH upon 1 plus GH. So this GH and GH, they will be cancelled out. So we are left with ET equals to 1 upon 1 plus GH RT. So this is the expression for the error signal. Now if we calculate the inverse Laplace transform of this signal, then it will be given by so taking the Laplace transform of this equation, we will get Laplace transform of ET will be ES, and Laplace transform of this 1 upon 1 plus GH. Laplace transform of G will be GS, and for H it will be HS. So it will be 1 upon 1 plus GS HS, and Laplace transform of RT will be RS. Okay. So this is the Laplace transform equation for the error signal. Okay. Now we will use this equation to calculate the error coefficients for the unit step, unit ramp and unit parabolic input. As we know that the unit step function it is also used for position, that is it is having constant position, and unit ramp function it is having constant velocity, and unit parabolic function it is having constant acceleration. So when we calculate the static error coefficients for these three input functions, then the error for the unit step function is known as the static position error coefficient. Okay, so for unit step function we are having the error coefficient named as static position error coefficient. For unit ramp function we will have static velocity error coefficient. For unit parabolic, the coefficient will be called static acceleration error coefficient. Okay, so for these three inputs we are having the three error coefficient named as static position error coefficient, static velocity error coefficient and static acceleration error coefficient. Now let us see that how we can calculate these error coefficients, what are their formulas. Okay, so let's start with the first static position error coefficient. The first error coefficient is static position error coefficient. This coefficient is denoted or represented by Kp. Okay, it is a coefficient K is there for this and P this subscript is for the position. Okay, and this coefficient, as we have studied, that it is associated with unit step input. So for unit step input, we know that RT is equals to 1 and RS will be equals to 1 by S. Okay. As we have calculated the error expression for the error signal, it was 1 upon 1 plus GSHS and multiplied with RS. Okay. So we will put the value of RS for the various input signals and then we will calculate the error coefficient. So here RS is 1 by S. So putting its value in this expression, we will get okay. So this was the error signal. Now if we want to calculate the steady state error, then steady state error is given by steady state error means we have to apply the final value theorem on it, and final value theorem says that ES it will be equal to SES and this we have to apply the limit as S tends to 0. Okay, so ES we have got the expression for it. So let us calculate the steady state error. We will have S, we have 1 by S here and then divided by this 1 plus GS HS. And here we have to apply the limit as S tends to 0. Okay. Now this S and S they will be cancelled out and we are left with only 1 upon 1 plus GS edges. So we will have to apply this limit S tends to 0 on this GS Hs. Okay, so we have got this steady state error value, and it will be equal to this ESS is equals to 1 upon 1 plus limit S tends to 0 GS Hs. Okay. Now this limit S tends to 0 GS Hs, it is the static position error coefficient. So Kp, that is the static position error coefficient, it is equal to limit S tends to 0 GS Hs. Now if we put this Kp here, so this steady state error, it will become 1 upon 1 plus Kp. Okay, and this is the position error coefficient. That is the static position error coefficient. So using this formula, we can calculate the static position error coefficient when the input is unit step input. Okay. Now the next static coefficient is static velocity error coefficient. Okay, so as we have studied that this static velocity error coefficient, it is associated with unit ramp function. And this static velocity error coefficient, it is denoted by Kv. K is the constant and V is the for velocity. Okay, so Kv, we can denote this by Kv, and it is associated with unit ramp input. Now for unit ramp input, we know that Rt is equals to T, and Rs, it is equal to 1 upon S square. Okay, and we have the expression for the error signal as Es equals to, so the expression for Es is 1 upon 1 plus GS Hs, and here we have Rs. Okay, now Rs, putting its value, it is 1 upon S square, so Es will be 1 upon 1 plus GS Hs and multiplied with 1 upon S square. Okay, so this is for Es. Now if we want to calculate the steady state error, then steady state error is given by again same formula, ESS equals to limit S tends to 0 SES. Okay, put the value of Es here, we will get ESS equals to limits S tends to 0 S dot 1 upon S square upon 1 plus GS Hs. Okay, this S, it will be cancelled with this, so we will have the steady state error as limit S tends to 0, and we were having here 1 by S, so this S will be multiplied inside and we will get 1 upon S plus S GS Hs. Okay, now this term 1 upon this S GS Hs, because this is 0, so we can neglect this sign and we will have only limit S tends to 0, 1 upon S GS HS. So this will become ESS equals to 1 upon limits S tends to 0, S GS HS. Now this term, this limit S GS HS S tends to 0, this is KV. That is the static velocity error coefficient. So we have KV as limit S tends to 0, S GS HS. Now if we put here this steady state error, it will become 1 upon KV. Okay, and this is the static velocity error coefficient value. By using this formula, we can calculate this velocity coefficient. Okay, so this is KV. Now the third error coefficient is the static acceleration error coefficient. Let's calculate it. We will have the third coefficient as the okay. Now this error coefficient, it is denoted by Ka. A for the acceleration. And this error coefficient is associated with unit parabolic input. Okay. Now for unit parabolic input, we know that RT it is equals to T square by 2. Okay. And RS will be equals to 1 upon S cube. Okay. So we have the expression for ES as 1 upon 1 plus GSHS multiplied with RS. Putting the value of RS here. Okay. Now steady state error. Okay. Putting value of ES here. And we are having here S also. Now this S, it will be cancelled with this. We will have square here. And then this steady state error will become okay. Applying the limits, this will become 0. So we will have the steady state error as 1 upon limits S tends to 0 S square JSHS. Okay. Now this denominator term, it is equal to the static acceleration error coefficient. So Ka is equal to limit S tends to 0 S square GSHS. Okay, and if we put here the value, then the steady state error, it is 1 upon Ka. Okay, and this Ka, it is the static acceleration error coefficient. So we have calculated all the three error coefficients, that is static error coefficient. First was the position error coefficient, second was velocity error coefficient, and third is the acceleration error coefficient, Kp, Kv and Ka. So these were about the static error coefficient. Now let us study about the dynamic error coefficients. Now, as we have studied that the static errors, they are associated with the standard input signals, that is unit step, unit ramp and unit parabolic function. Now, dynamic errors, they are associated with the signals which are changing with time. Okay, so there were two drawbacks with the static error constant. First drawback was that they do not provide information on the steady state error when the inputs are other than the basic signals. Okay, now second problem was that the error constants, they fail to provide or fail to indicate the exact manner or we can say that we express the error as a function of time. So there were two problems. So these were the two problems with the static error, that it do not provide information on the steady state error when the inputs are other than the basic signals. Basic signals means the unit step, unit ramp and unit parabolic. And also these error constants, they fail to indicate the exact manner in which the error is changing with time. Okay, so that is why we are using these dynamic error coefficient, because with the help of these coefficients we can express the error as a function of time. Okay, so consider a unity feedback control system. So in the unity feedback control system, we have derived that the Laplace transform of the error signal is given by the Laplace transform of the transfer function and the input signal. There means when we studied the static error coefficients, we were having ES equals to 1 upon 1 plus GS HS, and this was RS. Okay, so this was the transfer function, and here we were having the input. Okay, so TES, it is the error transfer function. This was the original transfer function, and this TES, it is the error transfer function. And this transfer function TES, it is given by 1 upon 1 plus GS. Okay, now putting the value of this TES here, And first, let us expand this by the Taylor series expansion. You have studied in maths that how we expand a Taylor series. By Taylor series expansion, this error transfer function can be expressed as so this is how we can express this TES by the using the Taylor series expansion. Okay, now putting the value of this TE in this expression for the error signal, then it will become ES can be expressed as multiplying the transfer function Taylor series expansion with the input signal RS. So we will have TE0 So we are multiplying every term with the input signal RS here. Okay. Now taking the inverse Laplace transform so that we will get the error signal ET. So taking inverse Laplace transform, we get inverse Laplace transform of ES is ET. Then we have TE0. Inverse Laplace transform of RS will be RT plus SRS will be R dot T. Okay, it's inverse Laplace. And then we have 1 upon 2 factorial. Then D2. Okay, so we have taken the inverse Laplace transform of this equation and we have obtained the expression for the error signal. So this is our dynamic error, because it can be calculated, or if through this dynamic error we are expressing this error signal as a function of time. And these coefficients, this, if we assume this TE0 and when we apply the limits on it, then we can write these coefficients as the dynamic error coefficients. So let's replace these with some constants. We will have ET equals to C naught RT Okay, so these C0, C1, C2, C3 and so on, they are called the dynamic error coefficients. And their value C0 will be equals to limit s tends to 0 TES, that is transfer function, and put the limits s tend to 0, then you will be able to get the dynamic error coefficient C0. C1 will be limit s tends to 0 differentiation of the transfer function with respect to s. C2 will be limit s tends to 0 double differentiation of this transfer function with respect to s. Similarly, C3 will be limit s tends to 0 triple differentiation of this. And for Cn, it will be limit s tends to 0. We have dn tes upon dsn. Okay, so this is the general dynamic error coefficients. By putting the value of n, we can calculate all the coefficients with the help of this formula. Okay, so we have calculated for a control system, we have studied the static error coefficients and the dynamic error coefficients in this video. So I hope this video is clear to you. Thank you.